effect of temperature on rate of reaction. Okay. So this can be given mathematically by Arrhenius equation. It goes this way. K is equal to A into e power minus EA by RT. Okay, where of course this K is rate constant or specific rate, then A is Arrhenius factor, collision factor, pre-exponential factor. Okay. Then this EA is activation energy. R is gas constant, and this of course is temperature. Okay, we'll discuss about this all in detail now, but before that let us take the mathematical thing, taking log on both sides. Right, ln I told you very clearly that when I write ln, it is log base e, natural logarithm, right? So it can be written as ln k is equal to ln a minus ea by r. Now converting this natural logarithm into base 10, normally I write this base 10 as simple log, log. So this ln or base e is equal to 2.303 log base 10, right? Now this can be written as 2.303 log a minus EA by RT, right? Now dividing by 2.303, we get log k is equal to log a minus EA by 2.303 R. Let me write it this way for convenience. Now come on. This can be given as y is equal to mx plus c, right? Now log k is taken on y-axis. This is the intercept. Then this of course is the slope, and this is x-axis. Let us plot a graph here itself. Plotted between log k and 1 by t, you get a straight line with a negative slope, with the y-intercept being log a, slope is of course minus EA by 2.303 R. Okay, then Let us take two different things. I mean, two different temperatures and two different rate constants. Okay. Now, see, log K2 can be given as log A minus EA by 2.303 R into 1 by T2. Just recall your memory with regard to your Clausius-Clapeyron equation. Same steps. Log K1 is equal to log A minus EA by 2.303 R into 1 by T1. K2 at T2. K1 at T1. Let me also tell you that the rate constant or specific rate depends only on temperature. Okay. Now, let us get the final expression. See, this can be written as log K2 by K1 is equal to, of course, this gets cancelled, and it can be written as EA by 2.303 R into 1 by T1 minus 1 by T2, or else log K2 by K1 is equal to EA by 2.303 R into T2 minus T1 by T1 T2. That's it. So this is, of course, the useful form of Arrhenius equation. Okay. Let me also tell you one very important thing, that is temperature coefficient. So this temperature coefficient is nothing but the ratio of two rate constants at two different temperatures. Differing by 10 degrees centigrade. Okay. Look at this. It can be given as K T plus 10 by K T. So this is temperature coefficient. In general, the value of temperature coefficient will be about 2. That means, see, the same thing can be given as, for every 10 degrees centigrade rise in temperature, rate of a reaction, or you can say rate constant, is almost doubled. Okay. See, it can even be 3. Lies between 2 and 3. The two temperatures normally considered here are 25 degrees centigrade and 35 degrees centigrade. So this is all about temperature coefficient. Nothing but the ratio of two different rate constants. You can say K2, K1. The two different temperatures generally considered are 25 and 35. The ratio is mostly 2. This can be even written as rate constant. Because when concentration of the reactants is unity, then rate becomes equal to rate constant. Okay. Now it is the effect of catalyst. So let us plot a graph between potential energy and the reaction coordinate, or you can say progress of the reaction. Look at this. See, this is the energy of reactants and this is the energy of the product. Now, because energy of the reactants is greater than that of the products, we can say that the reaction is exothermic, right? Now, this is called energy barrier. See, we get all this information in collision theory, of course, but because to explain the effect of catalyst, we need to discuss all this. Here itself, I'm going to tell you what activation energy is. Okay. Now, this energy barrier is what the reactants have to cross over because energy barrier indicates threshold energy, the minimum energy required to be possessed by the reactant molecules for their collision lead to the formation of products. Only when they cross this energy barrier, they can actually form the products. But because the reactants are just here, now in order to cross over the energy barrier, they have to be given extra energy. This energy, what has to be given to the reactant molecules in order to acquire a threshold energy is called activation energy. Now let me say that this is the activation energy for the forward reaction. If at all equilibrium condition is taken. Now look at this. So this is the delta H. Okay. Change in enthalpy. Now, as you know, for exothermic reaction, delta H is negative. Now, considering the backward reaction, this is the activation energy of the backward reaction. Okay. This is all when you don't have any catalyst. In the absence of catalyst. What all we have discussed till now is in the absence of catalyst. Let me write that. Now, what if a catalyst is employed? You know, a catalyst provides a new path for the reaction with a low activation energy. Now, see the height of the energy barrier is decreased. Now, this is the activation energy of the forward reaction of a catalyzed. Let me use a prime R dash, EA dash for the forward reaction. Then this one. So this is the activation energy for the backward reaction in the presence of catalyst. One thing very interesting about this is a catalyst not just lowers the activation energy of the forward reaction, but also lowers the activation energy of the backward reaction by the same amount. Look at this. By the same amount, if you observe, right up to this, you got the decrease. This is the decrease in case of forward. This is the decrease in case of backward. Okay. This activation energy is generally obtained because of the collisions that occur between reactant molecules. Okay. Catalyst provides new path for the reaction with low activation energy. See, in case of reversible reaction, catalyst lowers the activation energy of both forward and backward reaction by the same amount. And you might also be knowing that a catalyst is not at all consumed during the course of the reaction. It simply enters in one step of the reaction and goes out in the other step. Okay. So that is about the effect of catalyst. Next. Effect of radiation. See, there are certain reactions which show increased rate of reaction in the presence of light. Okay. Rate of reaction increases in the presence of sunlight. In case of some reaction. These reactions are called photochemical reaction. In case of which rate of reaction increases because of radiation. Let me give you an example. Formation of HCl from hydrogen and chlorine in the presence of sunlight. Okay. There are certain other things which also affect the rate of reaction. Like the pH of the solution. Let us consider an example. So this is ferrocyanide in the presence of thallium plus 3 converted into ferricyanide. Now this reaction takes place quickly or with appreciable rate in acidic medium. But does not occur in basic medium. This is how even pH also affects the rate of reaction. Coming to the effect of pressure. Pressure shows the effect in gaseous phase reaction. Okay, because gases are highly compressible. Even the electrical and magnetic field also affect the rate of reaction. Electric and magnetic fields will have effect when a reaction is carried out with a polar species. Polar, having charges. In such a case, it is affected by electric and magnetic fields. Next. Even the physical state of reactants also affects. In general, this is the decreasing order of rate of reaction. So reactions in gaseous phase occur very quickly when compared to the other states. It is because the collision in homogeneous system are more effective than heterogeneous system. Gaseous state is in fact homogeneous. Now coming to the size of reactant, even this also affects the rate of reaction. As the size of the particle is decreased, surface area increases. When surface area increases, rate of reaction also increases. Okay. Next. Even the dielectric constant of the medium also affects the rate of reaction. Suppose a reaction is taking place in polar solvents, or let us say the reaction is taking place between ionic compounds, then this dielectric constant will have effect on the rate of reaction. Greater the dielectric constant, greater will be the rate of ionic reaction. Okay. So these are the factors that influence rate of reaction.